All right, IBAISL2. Today we're going to continue with our work with probability, but today we're going to talk about independent and dependent probability. So the definition of when two events A and B are independent of each other is when one does not affect the occurrence of the other. This could be like, what's the probability that somebody rides a bike to school? And then the second event is, what's the probability that somebody has blonde hair? Like, those have nothing to do with each other. Like, if somebody's blonde, it's not going to change the probability of them riding a bike to school. So those would be independent events. The opposite of independent events are dependent events. And dependent probability means that if one event occurs, it changes the probability of the second event occurring. First example, this Venn diagram shows the number of students in a class who study Spanish. So S is for Spanish, and people who study math. M is for math. Determine whether S and M are independent events by calculating and considering the values of probability of S and probability of S given that M happened. So first let's calculate those things. The probability of S. Well, if I look at S, I see that within S there's 8 things, and then there's a grand total of 20 things in the entire space, like 6 plus 2 is 8, plus 3 is 11, plus 9 is 20. So S is going to be 8 out of the 20. Of course, you would want to fully reduce that fraction and call it not 4/10, but 2/5. Now, the probability of S given that M already happened. Now, M, if we look at it, is just 5 things. And then 2 of them are within S. So it's like 2 out of the 5. So this is 2 out of 5. I guess I could put 2 plus 3 since I was showing the adding. I'll keep consistent that this is 2/5. Now, because these two things are the same, you can say that these two things are independent events of each other. Part B. Calculate and consider P of S, or probability of S times the probability of M. And then we're going to find the intersection of S and M. So the probability of S, we already know, is 2/5 from the first problem. So probability of S is 2/5. Now probability of M is going to be 2 plus 3 out of 20. So that's 5/20, which is a quarter. Now if we're going to find probability of S times the probability of M, like they asked us to, that's going to be 2/5 times 1/4, which is like 2/20, which is like 1/10. So that's this part. That's probability of S times the probability of M. Then we're going to find the probability of their intersection. Now remember, the intersection is the space shared in between them. So the probability of S intersection M is 2 out of 20, which also equals 1/10. Because these are the same thing, this is an alternate way of showing that S and M are independent events. Example 13. So there's a survey where a bunch of adults are asked questions. One of them is if they like coffee. The other is if their name is David. You are given that C and D are independent events. Explain why this is the case. I mean, whether or not you like coffee or your name is Dave, like one's not going to affect the other. So you can just say, having, or should I say being named Dave? So, being named Dave does not have an effect on whether or not you like coffee, and vice versa. If you like coffee, that doesn't mean that the probability that your name is Dave changes. Given that probability of coffee is 0.8 and the probability of David is 0.007, interpret your answers in the context of each of the following. Well, because they're independent events, if you're trying to find their intersection, you can just multiply their respective probabilities together. So, because they're independent, this wouldn't be true if they were dependent, but because they're independent, this is probability of C times the probability of D, which is 0.8 times 0.007, which is 0.0056. Part 2. Their union. Okay, I feel like the book didn't do a great job of explaining why this is true, so I'm going to do a little picture for you guys. If you have two events where there's some overlap, where there is overlap between people liking coffee and people being named David, because there's a probability of an intersection. That means the probability of, we'll say coffee is here and David is here. If you're going to find the union, once again, is all of C and all of D. But notice with my shading that this part in the middle got double shaded. So if you were to just take the probability of C and the probability of D and add them together, you're double counting the coffee drinkers who are named David. So the way you fix this when you find the probability of C union D is you take the probability of C, you add the probability of D, but then you have to subtract out their intersection because the intersection is what got double counted. So this is 0.8 plus 0.007 minus 0.0056, which is about 0.8014. Part C says decide whether these two things are mutually exclusive. Excuse me. I feel like I already talked about this, that they do have an intersection. The fact that we found their intersection probability, you can say they are not mutually exclusive. And the reason for that is that the probability of their intersection does not equal 0. It would have to be 0 for them to be... sorry, I'm just cleaning up my writing. Their intersection would have to be 0 for them to be mutually exclusive. This Venn diagram shows the number of students in a class who can speak Spanish, Italian, and both languages, and neither language. There's 15 people that don't speak any of those, or either of those languages. We're going to choose somebody at random. S and I, so S is Spanish, I is Italian. All right, probability of S. Well, if you look at that, the probability of S is 7 things out of a total of 28. Is that right? Yeah. So this is 5 plus 2 over 15 plus 5 plus 2 plus 6, which is 7 out of 28, which is 1 out of 4. B, the probability of I. Somebody speaks Italian. Well, Italian is 8 out of the 28, which is 2 out of 7 if you divide them both by 4. Probability of S given that I happened. So the probability that somebody speaks Spanish given that they speak Italian. If it's given that they speak Italian, you're living just inside this sphere right here, and 2 of those people speak Spanish, so that's 2 out of the 8. Probability that somebody speaks Italian given that they speak Spanish. Well, that's the other circle, which means there's 7 Spanish speakers and 2 of them speak Italian. So this is 2 out of 7. Probability of I intersection S. Well, we can just see that in the diagram right here, that I intersection S is these 2 people out of 28. So that's 2 out of 28, which is 1/14. And then part F, probability of S times the probability of I. Didn't we already find those? We did. We found the probability of S is 1/4 and the probability of I is 2/7. So we can just multiply those together. Which is 1/14. Notice that their intersection and their 2 respective probabilities multiplied together are the same number. That means that S and I are independent events. Okay, you guys, good luck with your homework.